Well, hello. There we are. Okay, so we want to reflect it. So all of our y's are technically staying the same. What about these two coordinates? What's happening?
Invariant points.
They're invariant. Why are they invariant?
They don't move.
They don't change. And why don't they change? What's the y value there?
0.
The y value there is 0. And when I multiply 0 by negative 1?
It's also the line of symmetry. X-axis.
0.
The x-axis is the line of symmetry.
Of symmetry between the two graphs? Is that what you're trying to say?
Yes.
Sure. I'll agree to that. Okay, we don't ask that though. These little blue dots, the blue dots are the invariant points. Invariant point definition is it did not change. So sometimes people will tell me, if I do this, say I give you a graph like this. Awesome. And then we get a graph like this, like the reflection of it, or whatever it may be. They'll be like this, and then I do something and it goes like this. Just because it crosses doesn't mean it's invariant. Sometimes a coordinate will move onto a coordinate that already exists, but it moves to be on that coordinate. That's not invariant, right? Invariant means I apply transformations and nothing happens. They stay the same. That's what invariant is. So invariant points are those points. And why are they those points? Well, if I took wow, it's getting better. 1, 0. If I took 1, 0 and I took 1, negative 0, that's the same thing because 0 times anything stays a 0, right? So that's why we remain invariant. And we're reflecting on the what? Or reflecting in the what? Reflection in the what? X-axis. Exactly. That's where you're going. Okay, instead of saying reflection in the x-axis, what also is another word for x-axis? We talked about this already. Yeah, the line y equals 0 is the x-axis because that's where all the y's are 0. Okay? Then we have our other points. This one is at negative 1, 4. It becomes negative 1 and negative 4, so it's going to be down here. If I take more points and plot them correctly, is that better or worse? Better. The more points you actually take off of the original graph and apply and redraw, the more accurate your graph will be, right? Okay, now we're going to flip over. What are we doing on the next page? Something is way more fun than this class right now.
Comparing the negative x-axis.
I feel like they're doing the wave like in a hockey game or something. That's what it sounds like.
The line reflection on the line x equals 0.
Yeah. So this one here, we actually have a negative with our x this time. So if you think about it, we don't want to memorize, we want to understand. So if I'm taking an x that's positive over here, right? And I'm multiplying it by negative 1, it's now going to be negative, correct? And the negatives will be positive. So what does that mean? That means if I have a point here, it's going to be here. If I have a point here, it's going to reflect here. We agree? Because our negative, only the x's are being changed. The y height stays the same because my mapping is going to be xy becomes negative xy. And how do we know it affects the x? Because it's with the x. If it's in that bracket with the x, it affects the x's of the mapping every single time. What axis am I reflecting on this time when my positive x's become negative and negative x's become positive? Which axis is this? The y-axis. So whenever you actually have a negative x, you have a reflection in the y-axis. It's always about the opposite axis, but instead of memorizing that, why is it always about the opposite axis? Well, if my x's get negated, it's going to move from left to right, right to left, etc. My left to your right. And then it'll cross over that y-axis. If you don't know which one is which and you're guessing y-axis or x-axis every single time, do you think the test is going to go well? No, it will not go well. Okay? You need to know that if the x's are negative, it's a reflection in the y, and if the y's are negative, it's a reflection in the x, because it pops it over the x-axis, right? Okay, everyone's typing that one into their calculator. X squared minus 4x plus 4. Calculator one way. Then we're going back to grade 10 for a second. So we like to go back to grade 10 a lot. It's better than Narnia. That's why we go back there instead. So we type that in, and we actually get the same exact graph we did yesterday, right? It was that same graph. So we're typing this one in. So we get 2, 0 here and here, and then here and here. So this is f of x. Grade 10, ready? We always go back to grade 10. Grade 10 is the best of times. It was the best of times. There was no worst of times. It was the best. So in grade 10, your teacher gave you this. F of x equals, and it was normally linear. You're just putting down pencils. We're going back in time to grade 10. Okay, we're not writing this down. We don't care about this. We're just going back to grade 10, remembering what grade 10 is. So your teacher gave you this and said, don't freak out. F of x is just y. It's really hard to explain why you use f of x when you haven't even graphed linear graphs, don't even know what a graph is. But the reason why we now know why we use f of x or g of x or m of x is because you can have more than one graph on a Cartesian plane, and it specifies which one you're doing the transformations to, right? So we have f of x equals 3x plus 1. We agree? Now your teacher taught you that if we had f of 2 here instead, what did that just mean? X is equal to 2, because this is where x was, right? So what did you do in grade 10? You went 3 times 2 plus 1, and you found an answer of 7. What you actually found when you did that in grade 10 was a coordinate on this graph. That's all you did. 2, 7. 2 is the x, your answer is the y. So you found a coordinate, 2, 7. That is one of the coordinates on that graph. That's all you did. So you can put in a ton of inputs and get out a ton of outputs and do a t-table and have your graph, right? Okay, cool. That's grade 10. Grade 11. Actually, we're not in grade 11. Grade 12. What if I did this instead? F of A. What would I do? Yeah. All I'm doing is, instead of putting a 2 in for every x, I'm putting an A in for every x. So I'm going to this x, and remember, I'm replacing it, right? So I'm not keeping it with the x, like a tire, you replace the tire. So I would get 3, and then instead of x, an A plus 1. We agree? So they can put whatever they want in there. They can put a smiley face, and then you have 3 smiley face plus 1, right? That make you happy. All right, going back. So that's for grade 10. Grade 10 exists. Every single lesson in grade 10 existed so that you could be prepared for grade 12. Seriously, most of grade 12 lessons end with grade 10 material. Okay? I'll always go through how we did what we did, so it's not like you're going to just have to wing it. But it brings you back to what you learned in 10 and why you learned it, which is if I could sell to the grade 10s that that's why they're learning it, it'd be much better. But they don't believe you. All right. So instead of having f of 2 or f of a, this time they want the new y is just f of negative x. So what am I going to do this time?
Flip it on the x-axis or y-axis?
No, what am I going to do? Going back to what we just literally talked about. F of 2, I filled 2 in for the x's. F of a, I filled a in for the x's. F of negative x, what am I going to do to get my new equation? Fill the x's with negative x. And when you substitute in, you always put in brackets. Everything always goes in brackets the moment you substitute in. So I'm going to get negative x goes in for this x, but it goes in brackets squared. So that whole negative x is squared, right? Then I get minus 4 times negative x plus 4. See how I just put the negative x's in for x? That's all I did. And I put them in brackets. Now what we're going to do then is we're going to just apply that squared in because we can simplify this down. So our new equation is f of negative x, or y, whatever it may be, it equals x squared. Why is it a positive x squared? Because the negative x, the whole thing is squared, which is negative x times negative x, which is positive x squared, right? If you don't put it in brackets, your calculator, that was a number, your calculator would tell you it's negative, which it's not. And then I get negative 4 times positive x is positive 4x plus 4. Now type this into your y2. And then stop. So I want to show you something if you don't have the fancy colored one. So you have it in your y2. If you have the fancy colored calculators, you'll see two different colors of graph on your screen, correct? If you don't have the fancy calculators, the moment you press graph, the two lines are drawn, and then you press graph again. They will always draw the graphs in order. Y1 will be drawn first, then Y2. But once they're drawn, you press graph again, they both just pop up. So which one's Y1, which one's Y2? That's hard to do, right, if you don't have the colored one. So what I suggest, please pay attention, if you don't have the colored calculators, this is what I do. So in Y1, you will have x squared minus 4x plus 4. My calculator, if I brought it up, wouldn't be helpful anyways because it's a colored one. Y2 is x squared plus 4x plus 4. And I want to know that the second one is the transformed one, correct? But once I press graph, they draw them in order. This is true, but I press graph again, and now they're just drawn, and I don't know which one is which. So how can you tell which one is Y1 and which one is Y2? Go beside the Y2 over here. Every single person in Y2, arrow over. So if you don't have the colored calculators, you're following along. So you're going to arrow all the way over beside the Y2. There's a slashed line. Does everyone see that? So you're arrowed over here, and you're blinking on the slashed line. If you don't have a colored calculator. Okay, you're over there. Hit enter once. What happens? You get a thicker line, correct? Now press graph. So your first graph will be the thin line, and your second graph will be the thick line, and you can tell them apart. Now I'm going to break it for you, because if not, there will be two of you who will be doing this for the next 5 minutes, testing out all the different enters. If you hit enter, there's like a key looking symbol, there's a shading one, it shades above, it shades below, there's a dashed one. They are all useless to you, so don't spend the next 5 minutes ignoring me and trying to press that button and see what it does. I'm just going to, I'm coming into the movie and telling you all the other dice, that's what I'm doing. So don't do this, because what happens is 5 minutes from now, there will be one of you who will be like, oh, we're moved on, because you're still pushing those buttons. Okay? So don't be that person.
I already did it.
Of course you did. All right, so we got you through it, we can move on. So we're going to, did it reflect it in the y-axis on your calculator? Yes. So what's happening is, I have my mapping. xy becomes negative xy. Where are my invariant points this time?
0, 4.
Yeah, 0, 4, but why?
It's the line x equals 0.
Yeah. It's 0, 4 because that's where my x is 0, and if I times a 0 by negative 1, I still get that same number, right? That's why it's staying the same. Because now I'm multiplying my x's by a negative 1. So the only place my x will not change, the only number that you can multiply by negative 1 that does not change is 0. Right? If I multiply 1 by negative 1, I get negative 1. If I multiply 7 by negative 1, I get negative 7. If I multiply negative 8 by negative 1, I get 8. So the only number that does not change when you multiply by a negative 1 is 0. So I have to look for the spot where x is 0. So when I multiply by negative 1, it stays the same. So that's why on the y-axis, these are all remaining invariant, because that's where my x is 0. So this is my invariant. And then I'm going to use mapping to find the other. So now I have 1, 1. It's going to become negative 1, 1. And I know this is kind of monotonous, because you guys can do these, but remember I told you we're practicing mapping when it's easier, so that when it's harder we can do it. So my mapping was my x's became negative, so I'm just doing my mapping to this, and I'm applying a negative 1, and I get negative 1 and 1, and now I'm here, and I connect them. And then I use 2, 0, and it's going to become negative 2, 0. It's my new vertex. And then I have 3, 1, which is going to become 3 negative, negative 3, 1, bless you. And then I have 4, 4, which is going to become negative 4, 4. So it reflected, right? Also with that slash line, the moment you press delete or clear, like it clears out that equation, the slash line goes back to that normal thin one again. So you have to do it every single time. So here it says state the coordinates of the vertex while it's at, or the invariant points, not vertex. What's the invariant point at?
0, 4.
0, 4. Sometimes it asks you to state the coordinate of the invariant point. Sometimes it asks you to determine how many invariant points there are. Very different answers. Sometimes it'll say determine the invariant point in the form A, comma B, then list A, B respectively. Like sometimes it might be A, comma B, and then respectively. Respectively just means in that order. So my answer on my diploma would be 0, 4, right? Or it says how many invariant points there are, it would be 1. So very different answers. So you have to read really well to know if they want how many there are or what it actually is. And then in what variance of that do they want it. Here it says, how does the graph of y equals f of negative x compare to f of x? What happens when I multiply x by negative 1?
It reflects on the line x equals 0 y-axis.
So we say reflection in the y-axis. Make sure you write reflection in the y-axis. It has to be written in a proper way. It has to be written like that. Okay, you guys do this one quickly. Reflected in the y-axis. So we have xy becomes negative xy. So this one here, which is at 0 and, negative 4 and 0, is going to become 4 and 0. And then our 1, 4 is going to become negative 1, or negative 1, 4, sorry, is going to become 1, 4. So we connect it. This is invariant. Right? That's our invariant. Sometimes they don't ask about invariance. Sometimes they do. That's our invariant point. Why? Because it is at 0, 2, and then it will become negative 0, 2. They might say in a written response, they could say, the invariant point on this graph is blah. Justify why that is the case. And you have to explain why it's the case. Not just be able to go, oh, I know it's on this line. Justify why? Well, because the mapping of this equation is this. It is being reflected in the y-axis. When I use the mapping, the point coordinate stays the same, right? Because I'm multiplying a number by negative 1, and the only number that stays the same is 0. They have justifies. Justifies mean you have to explain why. That's why I need you to understand, not memorize. For all those justify cases on the diploma, or explains. And then this one here is at, that's terribly drawn one. That's not any better. Whatever. Okay, then we're going to flip over. Okay, I want you to sketch the following. What is this one going to do? It's a reflection in the x-axis. And what's my mapping? xy becomes negative xy, or xy becomes x negative y?
X negative y.
Why is it affecting the y?
Because it's reflecting on the 0 y line.
Yeah, but why is it a y? Because it's not with the x. Right, guys? Like if it's with the x, whatever's in here affects the x in mapping. If it's not in there, it affects the y in mapping. So for A, the negative is outside, and I say whatever's out here affects the y, and then whatever's in here affects the x. So it's going to be x negative y. And then B is a reflection in the y-axis. And once again, I have a negative x now, so it's going to be xy becomes negative xy. So if it reflects in the x-axis, that means we're doing this one. So our y's are being negated. This will remain invariant. If I ask how many invariant points there are, when this happens, people will tell me 2. Because for some reason you're drawn to bolded points. That's what you are. You are drawn to bolded points. There are not 2 invariants. How many invariants are there?
3.
There's 3. There's a bolded one, and then there's this little bad boy here that is not bolded, but still crosses through my x-axis and would still stay the same. So this one actually has 3 invariant points. Now, if I gave this to you as a daily quiz today or tomorrow, you will tell me it's 2. And we'll just have this discussion, and you'll still tell me it's 2. Because you're drawn to the bolded points. I get it. When they ask how many invariant points there are, they're not asking for, like, how many bolded points there are, right? So you have to find all the invariant points. Sometimes they'll just go and they'll label this like A, B, C, D, E, F or something like that, and they'll ask which ones are invariant, and you'll say A and F or whatever. And if they don't bold this one and give it a letter, then that one you wouldn't count. But they will bold it. Okay, make sure you count it. So these ones all stay the same. This one is at 1, 2, 3, negative 4, and 1, 2, 3, 4, 5, 6. So it's at negative 4 and 1, 2, 3, 4, 5, negative 6. This one is here, so it goes like this, boom, boom. And then this one is here, and back down. So that's this one. This one, we have a reflection in the y-axis. So how many invariant points do we have?
1.
1. It's right here. Then we reflect. This one's at 1, 2, 3, 4, 5, negative 6. So it's 1, 2, 3, 4, 5, 6. And then this one is at 4 and 6, negative 4 and 6. So now it's going to be at 4 and 6. And then we go here. And then this is at 1, 2, 3, 4, and negative 3. So it's at negative 4 and negative 3. Okay. Then here says the graph drawn in the thick line is a reflection of the graph drawn in the thin line. Write the equation of each graph drawn in the thick line. So the thick line is the new one. And we'll just assume, because they would have to label it, that this one is f of x. And so is this one. Or y equals f of x. Y equals f of x. Okay. Now some people say, I don't know where it's being reflected. Yeah. Yeah. If it is being reflected in one way, always look for where the invariant points happen, right? So for this particular graph, where is the point staying the same? On the x-axis. And now let's take an inspection of what that point actually is. So that point is approximately negative 1, 0. Correct? So which mapping would make that stay the same? Making my x negative or my y negative? My y negative would make that the same. xy becomes x negative y. This point would stay the same, and you can try it out. So you can go negative 1, 0 becomes negative 1, negative 0. So it stayed the same, right? Had I used the other version, though, negative xy, if I did negative xy, this would become 1, 0. And it would change it, right? So I know that this is giving me a negative y, correct? So it is a reflection in the x-axis. And if it's affecting my y's, it has to affect my y in the equation. So I'm going to get y equals, and I have 2 options. I can either put the negative in front of the f of x or the negative with the x. So the negative in front of the f of x or the negative with the x. Which did it affect? The y. So am I going to put it with the x? No, because then it would affect the x. So this is actually negative f of x. And when it's in front, it's reflection in the x-axis. Now this one has an invariant point on a reflection on the or in the y-axis. And if I compare my points, it would be x, y becomes
Negative x1.
negative x, y. And because my coordinate is 0, 2, it will become negative 0, 2. So I double checked it and it stayed the same when I did that, right? So I have a negative with my x. And if I have a negative with my x, it means it affects the x in the equation, right? So my equation then for this thick line is going to be y equals f of negative x. Because when it's with the x, it affects the x in mapping. When it's with the y, it affects the y. I want you guys to try and determine the equation if these reflections happen. Remember, if it's a reflection in the y-axis, it affects the x. If it's a reflection in the x-axis, it affects the y's. It's the opposite. So when we have a reflection in the y-axis, it affects the x's, correct? So the negative has to go with the x. So you should have y equals 10 to the negative x. When you have a reflection in the x-axis, it affects the y's. So you would put a negative with the y. Do they often write it in that form though? No, they'll do what? Divide by negative 1. And you don't keep the negative 1 on the bottom. It will just become negative root x. Which some of you may have written anyways. And we're going to flip over. We're not going to worry about this one because, yeah, we're not, because you don't know how to draw a rational. I want you to do this one, example 9. I want you to write out the new equation. And example 10, write out the new equation. Try them out. So, this we have a negative with the f of x. Is it affecting the x or the y? The y. So I can go negative y equals root x minus 2, and then I can divide by negative 1. And I get y equals negative 1 in front. Do I need the 1, or could I just put a negative sign? I could just put a negative sign. I wouldn't need the 1. Now this one is a reflection in the y-axis, but it's with the x. So I can put it with the x. So I take this x out, toss it out, and I put negative x in brackets. Do I actually have to have a negative x in brackets in this one?
Yes.
Would it affect it if I hadn't put the brackets? No. But if it was 2x minus 2, then it would make a difference, because you'd have to put the 2 in. So I always put in brackets anyways, and then I say, oh, the brackets don't matter, and then I rewrite it, and I go negative x minus 2. And it's fine. So that one, they gave you, remember this is just transformed form, correct? You cannot type that into your calculator, it has an F. We agree? That's just transformed form. This just means I have a negative that I have to apply to the function. This one here means I have a negative that I have to apply to the x's of the function. So these are the actual equations I can type into my calculator, right? Not those above. Those are just the transformations that they're telling us we have to apply. So they can give it to us like that. They can say y equals negative f of x or y equals f of negative x. And that means a reflection in the x-axis, and b means a reflection in the y-axis. Or they could give it to us in words, right? And ask the same thing. So here it says the equation of the reflection in the x and the y-axis. So if it's in the y-axis, it affects the what? The x's. If I have a reflection in the y-axis, it's my x's that are flipping, because they're moving from one side to the other, one side to the other, one side to the other. So that means I need to have a negative x. So it's y equals negative x squared plus 1, which is y equals x squared plus 1. This one, the equation of a reflection in the x-axis. So now this affects the y's. So I'm going to go y, negative y equals x squared plus 1. And then I divide by negative 1. What do I have to watch? Until now we've only had one term on the right-hand side. We applied the negative 1. You have to watch that every term is divided by negative 1. So I don't do the whole side by negative 1. When I divide, I will divide every term by it. So this actually becomes y equals negative x squared minus 1. So the last little bit of class, I have a little terms combined little thing to work on. And then tomorrow in class, you're just going to do the homework for vertical and horizontal translations and or reflection. So just the homework.